In the previous video, we were able to solve a number of ways to select a certain number of members from a certain multi-set. Okay, please try to review that previous video because you're also talking about a multi-set here, but in general sense. In the previous video, we're able to talk about or use actually the generated functions for specific items in our multi-set, and then combining them. And of course, as previously discussed, if we have here a sub n x to the power of n, a sub n is the coefficient. That means this is the number of ways, or this tells the number of ways of selecting n objects. Okay, so we had that previously. Now this time, as mentioned, let us try to generalize this on other types of multi-set, but in this time, okay, we are going to have infinitely many identical items, okay, in our multi-set. Because if we have finite number of items per multi-set, we can still use the previously discussed video. But for a multi-set, say for example, set M is a set containing infinitely many b sub 1 and infinitely many b sub 2, and also have here infinitely many b sub k. So we have infinitely many multiples for our items, still a multi-set here, and this time we're going to generalize the number of ways in selecting R members, and as of course a to the power of R, or actually it's not a to the power, pardon for this is actually a sub R for selecting R members. It's actually a sub R x to the power of R. We're going to solve for this item. Okay, not that item rather. We're going to solve the representation of a sub R for infinitely many identical items in our multi-set. So how did we do this previously? In our previous example, again, please try to review that. We use actually the generated functions for each of the given item in our multi-set. So for example, we have here b sub 1, they're infinitely many. So we can actually write the b sub 1 or the infinitely many b sub 1 using this given sequence, okay, or generated function. So for this, we have here, say for example, 1 plus x squared plus until you reach a certain value, which is again infinitely many, so we don't know what is that. This tells us that b may not be selected depending on what is our R. B sub 1 rather may be selected once, b sub 2 may be selected once, okay, or so on and so forth as well. Okay, so that's the first possibility for our b sub 1. Supposedly we are using, in the previous video we have here bx and b like that, but since we are generalizing that, let's talk about this as our for b sub 1. Now for b sub 2, okay, so we're going to multiply the possibilities according to multiplication principle. You have 1 plus x squared plus still the same. That's for our b sub 2. Now for most of the items here will be just the same because we have infinitely many items per quality in our multi-set. It will end up in 1 plus x squared plus dot until your b sub k. Right? So how do we identify the representation for a sub R here? We can actually look into the idea for all of this, because each of this generated function can be written as a rational expression. You have actually 1 over 1 minus x. This is the reason why we keep on repeating that this identity is very important. If you have sequence like this, it's just equal to 1 over 1 minus x. We have proven that identity as well in this playlist, and that will be used again just like this one here to prove other relationships. So that's for b sub 1. For b sub 2, it also looks like that. So you have 1 over 1 minus x, and all of the entries here would be the same until you will get here to 1 over 1 minus x for your b sub k as well. In short, how many 1 over 1 minus x are multiplied? Take note, there are b sub k, so there are k number of elements, distinct elements that are multi-set, having infinitely many multiples or duplicates. So this time, we can actually rewrite this into one form, 1 over 1 minus x raised to the power of k. Right? take that our goal again is to find the a sub r to be paired with x to the power of r for this type of situation. So we have yet to identify that, but we know something here. Okay, we can actually write it in this manner. As we distribute the exponent, you have 1 using the power, the 1 to the power of k, and 1 minus x to the power of k, which will give us 1 over 1 minus x to the power of k. And this can be written as 1 minus x to the power of negative k. According to the generalized or the generalization for the generalized binomial theorem, if you have a situation like this, but for that binomial theorem, we actually had 1 minus x raised to negative n. In this case, n is k, or k is n. We can actually, what do you call this one, express this also as a sum of different forms. This is actually illustrated as 1 plus, you have here 1 plus n minus 1, combination 1 for our x, okay, which will actually return to this, but we will not return to that because that's not our concern. Plus, you have 2 plus n minus 1, combination 2 for your x squared, until you reach r plus n minus 1, combination r for our x to the power of r. Because if you're going to use this identity, noticeably, x to the power of r is already there. It appeared here. That's the coefficient where, or the little coefficient for our numerical coefficient, the item we're looking for as a generalization for the formula. So let's just simply transform this here, this one, as this form. So instead of n, we will be having k. So we will have here 1 minus x to the power of negative k, which will be equal to this expansion 1 plus, we have here 1 plus, instead of n here, we'll be using k because that will be our exponent. N is equal to k. So k plus 1 combination, minus 1, combination 1 for our x, plus 2 plus k minus 1, combination 2 for our x squared. And then you will reach here a certain form of r plus k minus 1, combination r for our x to the power of r. Again, our task is to identify the numerical coefficient for this, which stands for a sub r for our general formula whenever we have a multi-set that has infinitely many multiples for each of the quality of the elements there. So we will have the formula. But what is that formula? It's actually, again, because we are looking for a sub r x to the power of r. So a sub r is actually this form here, which stands for r plus k minus 1, combination r. So if you are just asked about the number of ways of selecting r members, regardless of what that r is, from the multi-set where the number of duplicates for certain items are infinitely many, simply take out this formula where r, again, is the number of members you're choosing from the multi-set. K would be the number of distinct objects from that multi-set, and then minus 1, combination r. This is the formula we'll be using for this specific type of situation. Okay, so take it again. A sub r is r plus k minus 1, combination r. Thank you very much for watching.